Hello everyone. Today I'd like to introduce you the black-white bakery errorism. This is one of the errorism to solve mutual exclusion. But first, let's take a look at bakery errorism. The bakery errorism has two shared variables. The first one is the Boolean array choosing of size n, where n is the total number of processes. Initially, on element of choosing has value phone. And the second variable is the number array, also have size n, and its values is from 0 to infinite. Initially, on element has value 0. If process I want to enter vertical section, it first gets through the doorway, and in the doorway, it says it's choosing to true to announce order that I'm enter the doorway, and then it's calculate the maximum number of number array and set to its number as 1 plus maximum, and recess is choosing to phone and enter the waiting part. Please be noted that in the waiting part are using different statements rather than what we have in our lecture, but you can imagine that a wait condition is equivalent to while not condition do skip. So first, process I have to wait until choosing chase is phone, which means chase doesn't contain for vertical section, or it exits the doorway and now also looping in the waiting part. Then process I have to wait until number chase equals 0, which means chase already exists vertical section, or at the beginning it doesn't contain for vertical section at all. And the number of i's is smaller than the number of chase, which means I has higher priority than j. Okay, now let's take a look at what property bakery errorism satisfies. First, it satisfies fivefold fairness because you can see that the sooner a process enters the doorway, the smaller its number values, and then in the waiting part it will have higher priority. But it doesn't satisfy local spinning because here it's been on the choosing and number j, which is the shared variable and doesn't exist in its local memory. It doesn't satisfy adaptive as well because the algorithm has time complexity depending on n, the total number of processes. An algorithm only satisfies adaptive if its time complexity depending on the total number of contending processes, and it isn't bounded because its value can be up to infinite. Next, I will introduce the black-white bakery algorithm. It is also a mutual exclusion algorithm. Black-white bakery algorithm using one additional share bit called color, and it can have values either black or white. It also introduces a ticket array of size n. Each element has a pair of color which have the value black or white and a number from 0 to n. Initially, on choosing element are phone and all number has value 0. On ticket color and the color bit has the same color. The ticket element can be ordered as the follow rule. First, if two tickets has the same color, the ticket with a smaller number is smaller and have higher priority. In case two tickets have different color, the ticket that have the color different than the color bit is smaller and have higher priority. Let's take a look at the example. We have three tickets. Ticket A with the value white and 1, ticket B white and 2, and ticket C black and 1, and the current color bit is white. If we compare ticket A and ticket B, since they have the same color, it will consider the number and see that A have the smaller number than ticket B, then ticket A is smaller than ticket B. And if we compare ticket A and ticket C, since they have different color and ticket C have the color different than the color bit, then ticket C is considered smaller and have higher variety. In other words, ticket C is smaller than ticket A and smaller than ticket B. So, if 3 tickets currently looping in the waiting part, ticket C can enter the critical section first, and then ticket A, and then ticket B. Okay, now let's get back to our algorithm. If process I want to access critical section, it first must get through the doorway. First, it set its choosing value to true and change its color ticket as same as the current ticket bit. Then it calculates the maximum number of the ticket which have the same ticket color and then set to its number as 1 plus the maximum number. And then it resets its choosing value to phone and enter the waiting part. In the waiting part, process I first waiting for the choosing chase equal phone. It means chase either doesn't contain for the critical section or is already get through the doorway and currently looping in the waiting part. Then it checks if they have the same color. Then ticket A will wait until ticket J doesn't contain for the critical section anymore. Or ticket I has smaller number than ticket J, so I has higher priority. Or ticket J re-enter the doorway. In case they have different colors, then process I will wait until process J doesn't contain for critical section anymore, or process I has higher priority because it have the color different than the color bit, or process J re-enter the doorway again. When process I exits critical section, it will set the color bit to a value which is different than its current values. And by doing that, it gives priority to awaiting processes that hold ticket with the same color as the color of each ticket. For example, if ticket C exits critical section, it will set the color bit to white. And by doing that, all tickets that have the color black will have a higher priority than the ticket have the value white. I also want to emphasize that the last condition here is quite important and cannot be eliminated because it may cause deadlock. For example, if we have ticket A and ticket B currently looping in the waiting part, and since ticket A has higher priority, it can enter the critical section first, and after exit critical section, it will change the color bit to black. And maybe ticket A re-enter the doorway again, and then it will have new values with the color black and the number maybe 1. And since at the beginning ticket B already checked its color with ticket A and they have the same color, so ticket B always loop in this condition. It never get back to check the color again, it just keep looping in this condition. And now ticket B see that its number values is higher than the number value of ticket A, so it's considered that ticket A have higher priority and waiting for ticket A to enter critical section first. In the meanwhile, ticket A will check that it have different color than ticket B, so ticket A will loop in this condition and see that because ticket B have different colors than the color bit, so it's considered that ticket B have high priority and waiting for ticket B to enter the critical section first, and this situation can create a deadlock. Now let's check with property that the black-white bakery algorithm can satisfy. First, it satisfies first in first out fairness, but it doesn't satisfy local spinning because you can see that in the part it's also spinning in the shared variable which doesn't exist in its local memory. It doesn't satisfy adaptive as well because the time complexity is depend on n, the number of total processes. However, it is bounded because the number can only have the value up to n. Next, we will consider the black-white bakery algorithm, which also satisfies adaptive. The adaptive black-white bakery algorithm introduced a new active set called S. Initially has value empty, and together with the set S, we also introduce three operations, namely join S, leave S, and get set S. For join S, we add the ID of the executing process to set S. For leave S, we remove the ID of the executing process from set S. And for get set S, we return the current set of active processes. The basic idea here is to use the active set object in order to identify the active processes and then to ignore the other processes. But please be noted that we have two communication models which have different definition of the remote access. For the first one, distributed shared memory model. Any remote access causes communication. And for the second one, coherent caching model. A remote access to resistor R causes communication if the values of R is not the same as the values in the cache. And for this version of black-white bakery algorithm, it's only adaptive for coherent caching model. If process I want to access critical section, it must get through the doorway, and in the doorway, first we ask process I into active set S, and then set its choosing value to true. Then we read set S into the local memory of process I, and then set its ticket color as same as the color bit. Next, we calculate the maximum number of ARM processes in local S with the same ticket color as process I. And then we set number I is equal 1 plus the maximum number. Then we reset choosing to phone and update local S. For the waiting part, we look for ARM processes in local S. The remand is similar to the previous version. After existing critical section, we remove S out of the active set S, and we can see that this version of black-white algorithm satisfies first in first out fairness, but it doesn't satisfy local spinning because just like previous version, the spinning of these variables also in the shared memory. For adaptive, this is adaptive for coherent caching model because the algorithm have time complexity depending on the active number of processes. And the variable here is considered as only one remote access if its values is as same as the value in the cache. However, it is not adaptive if we using distributed shared memory because for distributed shared memory model, any spinning here is considered as remote access no matter which value is returned, and it's also satisfied about it. That in bakery algorithm, we use single writer self-resistor, but in this algorithm, we use multi-writer resistor and atomic resistor. We also have the two following theorems. The first theorem, there is no adaptive mutual exclusion algorithm in both the coherent caching and the distributed shared memory models if resistor accesses are non-atomic. And the second theorem, there is no adaptive mutual exclusion algorithm in both the coherent caching and the distributed shared memory models using only single writer resistor. For now, we've seen the black-white bakery algorithm that satisfies first in first out fairness, bounded, and adaptive for coherent caching model. The original paper also introduced a next version of black-white bakery algorithm, which also satisfy adaptive for distributed shared memory model and local spinning, but this is out of scope of this presentation. So if you find the topic interested, you can figure out more in the original paper. Thank you for listening.